Hello everyone. I hope I'm audible. Okay, thank you. So today I'm going to take you through mathematical foundation. I think this is our first tutorial on mathematical foundation. So what I want us to look at maybe as an introduction, we're going to look at set theory. That's what we're going to look at. We're going to look at set theory, but we are looking to cover maybe 3 to 4 topics on this one. Maybe I just want someone to help me to admit those who are still want to join, so that I won't switch back and forth. Also, maybe it would be good if I also talk about the basic ground rules. So guys, on the issue of rules here, it's just like, let's make sure that we are always on mute. If you want to say something, please do so. Please do so by just raising your hand. And if you just raise your hand, then what I will do is I will pick you. But if I feel like I still, but if I fail to pick you, then you can just interrupt. There's no problem with that. You can just interrupt. There's no problem with that. Okay, so now let's hello. Okay, so now let's look at the issue of sets, right? Want to look at the issue of set theory. Let's look at the issue of set theory. So normally when you are talking of sets, I just need maybe a pen rather than a highlighter, right? Let me have a pen. I need a highlight. Guys, who is going to help me to accept those who wants to join? I don't know who is going to help me here on this issue. Maybe someone could just raise a hand and then I'll pick you. Just give you the rights to do so. Okay, let me just continue with the. Okay, thank you, Wilfred. Let me just make you a presenter there. I hope you'll be able to do that. Maybe I'll pick 2. So please help me to do that. I hope you'll be able to accept all those who want to join. Thank you for that. Okay, so you can lower your hands. I think the issue is now resolved. So now let's look at the issue of sets. Let's now look at the issue of sets. I just wanted a highlighter rather than a pen. Maybe I'll stick with that color. Okay, so you have done this before. Maybe at O level, at A level, you have done sets, right? So it's just the same as those that you have done, right? Only that we are required to do that as well at this level. So let's look at what is a set. So in general, a set is any well-defined collection of objects. So if we have a collection of objects, we can call that this one, it's a what? It's a set, right? So the elements of a set are the objects in a set. Just like we have got a set of students, right? And then what makes up this set that we call student? So those actual students are now the elements of that set, right? So any well-defined collection of objects can be called what? A set, right? We can have a set of computers, and then those actual computers will be the elements that makes up that set. So take note of that technicality when you're talking of this. Normally that's what we'll be talking about. If you hear about elements, about a set, those are the perfect definitions for that. And then there's what you call the set notation, the ways that we use to denote a how do we call it, to denote a set, right? So normally we denote sets with uppercase letters, elements with lowercase letters, like the following notation is used to show set membership, right? So there is basic set notation that you need to know, so that whenever you see that, then it won't be an issue, right? Like here, if you say x and this symbol and then a, so a will represent the set, x will represent the element, right? So we are saying x is an element of a, which means x belongs to a, or x is a member of a, something like that. And then for this one, we'll be saying x is not a member of a, just like that, right? By using this symbol. That's what this symbol actually mean. Just want to check if people are being accepted. Thanks. So basically, that's what does this mean. So normally we denote the set by using this capital letter A or capital letter B, whatever, something like that, and then the small letters for the elements. Then there are ways of describing sets. This is also a very, very important thing that you need to really understand. Why? Because sometimes you might be given a set in some way, right? And then you'll be required to answer maybe the following questions. So you need to know these ways of describing sets. Like here, there's what we call a roster method, which is the most popular way that we used to see. We'll be given maybe the set name, and then you are given the elements inside this bracket, something like that. So you are being the roster method is this one where you will list the elements, right? So what it means that the set A will contain 1 2 3 4 5 6 as elements or as members of A, right? Something like that. So that's what is happening here. So it must be something which is very, very simple to you. Then there's what you call a set builder notation, right? What does this mean? So this is also the other way that you really need to understand, and it's very, very important. Why? Because you might be failed to answer the following questions by not understanding what does this mean, right? So characterize all those elements in the set by stating the property or properties they must have to be members. So in other words, you are given a statement which needs to be satisfied by an element for that element to be the part of that set, something like that. So you read it like this, right? You are given x such that x is an odd positive integer which is less than what? Less than 10. So in other words, we are saying x such that x is an odd positive integer less than 10. So we are taking all odd positive integers which are less than 10 to be the members of what? Of this set. So we are saying set A have got a member called x, such that this member we call x must be an odd positive integer which is less than what? Less than 10. So you find all the positive in the odd integers which are less than what? Less than 10, and those are the ones that makes up this set. So it's you who will be required to come up with those elements, and maybe might be then there might become some follow-up questions, right? So it's up to you now to understand this technically, or this way that we call set builder notation. And then there is also this descriptive form where you'll be given a verbal description, like here x is equal to a is the set of all integers from 1 to 6 inclusive. So in other words, now you need to find all integers from 1 to 6, and it is being said to be inclusive, right? So you need to know about the boundaries, what you are talking about the boundaries, something like that. So basically, this is another way that you need to really understand when it comes to the formation of sets. How do you form sets, something like that, right? So please, let's make sure that we really look into this. And sometimes it's also very, very important to know what are integers, right? What are prime numbers, right? Why? Because those things, you find them being used in a set. So you need to know those set of integers, set of real numbers, set of something like that, set of prime numbers. Those are about perfect squares. Why? Because sometimes you might be given that as a technicality that maybe we were saying integers 1 to 6, maybe we'll be talking about perfect squares or whatever, something like that. So you really need to know. So common sets of numbers that you really need to know: the set of natural numbers, the set of integers like this one, also the issue of rational numbers, the set of real numbers, the set of complex numbers, something like that. These are basic things that you really need to know, that not maybe knowing deeper, but just knowing that if you are talking of a complex number, there's a real part and imaginary part. Okay, if you are talking about the set of real numbers, what are these real numbers, the counting numbers, what was something like that. That's what you just need to know, right? So let's talk about some special sets. So there are special sets that that we do have when it comes to set theory, right? And we can first start at what we call a null set or an empty set, right? So this is a special set, and there is a reason why we have it here. It is very, very important for you to know this. Let's make sure that we are always on mute, unless if we really want to say something, right? So when it comes to the issue of special sets, we've said that we've got the null set or an empty set, right? So this is a set with no elements, often symbolized by this, some sort of a phi, or this one a circular with what, with a strike, or just these empty curly braces, something like that. So this means that the set is empty. What is this empty set? It's just a set without any element, set without any members, something like that. And then there's what you call a universal set. This is the set of all elements currently under consideration, and is often symbolized by this U or this symbol. Normally that's what we normally use to represent those the universal set. So all the elements under considerations, or the population that you're talking about, that's the universal set, something like that, right? Then let's talk about the membership relationships. Let's talk about the membership relationships. Let's make sure that we are always on mute. I don't know those who are muting unmuting themselves. Okay, so let's look at what we call a subset, right? So if we have this symbol that we have here, which says A is a subset of B, what does it mean when you say A is a subset of B? What's the relationship between A and B, right? So we say A is a subset of B if X is an element of A. Like we are taking some element that we say is what is in A, and also implies that that element is also in a B. So that is that all the members of A are also members of B. So the notation for a subset is very similar to the notation for less than or equal to, and means in terms of the sets included in or equal to. So in short, we are just saying if you have got A and all the elements of A are found in B, it means that A is a subset of B. Why? Because every element that we have in A is also part of what? Of set B, something like that, right? We can talk of like we have got a set of students, right? Those students doing what? Doing IT. Maybe something like that, students doing IT and software engineering, right? But if we take those who are doing mathematical foundation, you find out that this will be now a subset of those students that we have been talking about, those students doing IT and software engineering, something like that. So if you say, now we have a special set which needs students who are just doing mathematical foundation, which means maybe we have those which are not doing mathematical foundation, but they are still doing IT. And then we've got those which are doing mathematical foundation, but they are still doing what? Doing IT, something like that. So that's the kind of relationship that we are talking about. And then there's what we call a proper subset with this one. So A is a proper subset of B. We say A is a proper subset of B if all the members of A are also members of B, but in addition there exists at least one element C such that C is element of B, but C is not an element of A. So the notation for subset is very similar to the notation for less than. So when I talk of this, right? So we have got a proper subset and a subset, right? So this one is as good as A and B are equal, say something like that, right? A is a subset of B, but we do not have a C, which is not part of A, but it is part of B, something like that. So when you are looking at a proper subset, that's where we have maybe something like this, and then we have something like this, where this inner part is A and then the outer part is B. It means that A is a proper subset. Why? Because we've got elements which are in A, which means all those elements which are in A are also in what? In B. But there are some other elements which are not in A but are in what? Are in B. So these sets are not even equal, right? So we say this is a proper subset. Why? Because A is not even equal to B and cannot be equal to B. So that's the proper subset, something like that. Then there's what we call finite and infinite sets. It's just from this keyword, right? If it is a finite set, it must have a limited number of elements. But if it is infinite, it means that it goes up to infinity, something like that. So a set is said to be finite if it contains exactly m distinct elements, where m denotes some non-negative integer. In such case, we use this some sort of this modulus, or the number of elements in a set S is equal to m, something like that, or the number of elements in S is equal to m, which is the cardinality of set. We call it cardinality of set, something like that, right? So a set is said to be infinite if it is not finite, or if it is not finite, something like that. So the set S of letters of English alphabet, is finite. Why? Because the number of elements in it, A to Z or A to Z, is just 26, right? So it's finite. But the set of positive integers is infinite. You can read from 1, 2, 3 going, I don't know, right? So it's infinite. So that set, we can say that we do not have the exact total elements, something like that. Then let's talk about those sets which are equal, right? What are these sets that we call these sets are equal, and how do you determine if these sets are equal, something like that. So normally when we look at this issue of sets being equal, two sets are equal if and only if they have the same elements, right? So we say these sets are equal if they have what? The same elements. So the issue is around the issue of what? Of having same elements, just like that. Therefore, if A and B are sets, then A and B are equal if and only if, for all this one you call it, for all of X is an element of A, also it implies that X must be also an element of B, something like that. So we write A is equals to B if A and B are equal sets. Okay, so the sets 1, 2, 5 and the 2, 5, 1 are equal because they have the same elements. If you look at it, we've got element 1, 2, 5, and also we've got 2, 5, 1, which means 2 is part of this set and 5 is part of this and 1 is part of this, something like that. So these elements are equal. So the arrangement, the order is not necessary there. Also, the order in which the elements of a set are listed does not matter, something like that. So also it does not matter if an element of a set is listed more than once. So if you have 1, 2, 2, 2, 5, 5, something like that, this set is just the same as this set. And normally when you are writing, we do not repeat. So this set is just one set because we've got same elements. Then there's what you call Venn diagrams. This is what you have been doing at O level, A level. We have been doing Venn diagrams, right? So what are these Venn diagrams? So these Venn diagrams that we see here is some sort of called Venn diagram because of one reason. There was this English mathematician called John Venn who introduced these diagrams. So in Venn diagrams, the universal set U, which contains just what a little, I think I need to take this core. I need to take this core. Comrade Madi. Mushe niborum jagamatu kuti. Okay, iri bondo okufonera. Sure. Okay, so was saying that so in Venn diagrams, the universal U, the universal set U with this symbol that we've been talking about, which contains all the objects under consideration, is represented by a rectangle. So these are basic way of writing whatever, of drawing Venn diagrams, right? So I do not want to ask you later that where is that the representation of a universal set. So you need to know that you need to put this rectangular shape to represent the universal set. This is just the norm. So do not draw a Venn diagram without that rectangle. I think we agree on this. Then inside this rectangle, you need to have circles or other geometric figures which are used to represent sets. So normally we will have a circle to represent a set, maybe calling this set A, then you have another circle, set B, whatever. The way you arrange those sets or circles, it depends if they are sharing elements or sharing members, something like that. So it's the one that determines that issue of how you arrange those circles, something like that. So then the Venn diagrams are often used to indicate the relationships between sets, like what I've said. Normally we want to see which elements are in A, which elements are in B, which elements are in D, something like that, right? So there's what we also call a power set, right? Given a set S, the power set of S is the set of all subsets of the set S. So when I talk of a power set, you need to know this, right? We are talking of subsets, and we are talking of all possible subsets of that given set. That's what we call a power set. So the power set of S is denoted by P of S, right? So if it is power set of Q, it will be P of Q. So what is the power set of the set 0, 1, 2? There's the other thing that you need to know. An empty set is also part of that power set. You need to know that. Why? Because an empty set is a subset of each and every set that you can have. Okay, so we've got 0, 1, 2 as elements in this set, right? So how do you find the power set, right? So you need to find all the subsets or all the possible sets that you can have from this. So we start with the empty set as the first subset, and then you can take 0 as a subset, 1 is a subset, 2 is a subset. Then you can take a set with elements 0, 1 alone, or the one with the 0, 2 alone, and then the one with only 1, 2, and the one with the 0, 1, 2, something like that. So if you look at how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, right? So this completes our power set. Why should I have to count that? Are they up to 8? I've got 1, 2, 3, right? So it will be 2 to the power 3. If you want to find the total number of subsets that you can have from that set, it will be 2 to the power number of elements, right? So if you are being asked to find the total number of subsets that you can find, that you can have from this set, note that it's just 2 to the power n, where n is the total number of elements in that. So 2 to the power 3, I think it gives me 8, right? So that's why I've counted from 1 to 8. And take note that the empty set is also a subset of a what? Of any given set. So it should be part of a what? Of a power set. You need to know that. I'm trying to stress that so that you get it. Then there's what you call a Cartesian product. Normally when you are talking of Cartesian product, it's not like you are just multiply. We see it. Why am I saying so? So let A and B B sets, right? The Cartesian product of A and B, denoted by A cross B, is the set of all ordered pairs A, B, where A is an element of A and B is an element of B, right? So this is just the shorthand of what we are talking here, of what we are talking about there. So I just need to change this color maybe to just green. Okay, so what is the Cartesian product of A and this set B? The Cartesian product of this set A and this set B. So if you want to find A cross B, what do you do? Or the Cartesian product. So what you do is you pair 1 with all the elements in B and you pair 2 with all the elements in B, like what we used to do when we are just expanding brackets in algebra, something like that, right? But you see that it is going to be a little bit different when you are dealing with maybe given 3 sets, if you want to do the cross product of 3 sets, something like that, right? So if you look at it here, you'll be saying 1A is like this, you take this and this, then 1 with the B, then 1 with the C, and then you go 2 with the A, 2 with the B, 2 with the C. So this will be your cross product or your Cartesian product, something like that. And you need to know that AB or A cross B and B cross A are not equal unless if A is an empty set and B is an empty set, so that A cross B will be just equal to an empty set. Or if A and B are equal, that's when, or that's only when A cross B and B cross A are equal. Otherwise, if you are going to find B cross A here, you are going to have A1, maybe A2, B1, B2, C1, C2, something like that. So you are now interchanging, right? So here A and B, or the X, Y, whatever, the domain and the range is now interchanging, something like that. So what if you've got, you are supposed to find a Cartesian product of sets A up to sets an, something like that, right? Like what I've said, that maybe now you are given 3 sets, right? 4 sets, something like that. How do you do that, right? How do you find that Cartesian product? So let's do it when you're given 3 sets, A cross B cross C, something like that. How do you find the Cartesian product? This is very, very important. So how do I do? I have this and this and this, right? And I'm supposed to find A cross B cross C. So the Cartesian product of A cross B cross C consists of all ordered triples, which is A, B, C, where A is an element of A. So we're going to have at first we're going to have A, which are all the elements of this set A, and then here we are going to have the elements of set B, and then at the last part we're going to have the elements of set C, something like that. So that's what you are going to have. I just want to check if the person that wanted to log in was actually accepted. Okay, so now let's look at this. So how do you do it? First, we are going to work with this 0, right? We're going to work with this 0. Then we cross it with everything here. So how do you do it? Maybe let me can I have an eraser there? I just want to take this out so that okay, so what we are going to do is we are going to take this 0. What do you do next? So it says 0, 1, 0, something like that. That's the first part that we have here. Then the next thing you say 0, 1, 1. So you take 0 and pair it with 1 with everything in C. So it's 0, 1, 0, 0, 1, 1, then 0, 1, 2, up to here. After doing that, since we have paired 0 with 1 and everything in C, now we pair this 0 with a 2 and everything in C. So I'm going to say 0, 2, 0. That's why you've got this. Then 0, 2, 1. That's why we've got this. And then 0, 2, 2. That's why we've got this. And then after that, since we've paired 0 with both with 1 and everything, and 0 with the 2 and everything in C. So the next thing that we are going to do is to pair this 1 with the 1 and everything in C, and this 1 with the 2 and everything in C, something like that. So we are going to have a 1 and a 1 and a 0. That's why I've got this. Then 1 1 1. That's why I've got this. Then 1 1 2. That's why I've got this. And then after that, since we've paired 1 and everything in C, so we pair 1 and 2 with everything in C, something like that. So we'll be saying 1 2 0. That's why I've got this. Then 1 2 1. That's why I've got this. Then 1 2 2. That's why I've got this. So that's the cross product of A cross B and cross C. I don't know if there are issues or if there is any need of clarification on how do you do this cross product given 3 sets. If there is any issue, please raise it now. Otherwise, you run into a problem you want to do, or just reference to this video, so you can reference to this video. Okay, so now let's look at the issue of set operations, right? How do you do these set operations? So 2 or more sets can be combined in many different ways, right? So for instance, starting with the set of mathematics majors at your school and the set of computer science majors at your school, we can now form from these sets the set of students who are mathematics majors or computer science majors. Also, we can form the set of students who are joint majors in mathematics and computer science, or the set of all students not majoring in mathematics, something like that, right? These are kind of operations that you can do on a set. So now let's talk of set union, what we call set union. So A union B is the set of all elements that are in A or B or both. So when you are talking about A union B, you are taking all the elements in A and the elements in B, then we put them in one set, and then we call that this set is A union B. So an element X belongs to the union of the sets A and B if and only if X belongs to A or X belongs to B. So you are looking at those elements which belongs to A or which belongs to B. I think it's very, very simple and very, very clear and straight to the point. So when you are being asked to shed the set A union B on S or what do we call it, on a Venn diagram, what you do is, now we've got set A, this one is set A, right? This part is set A, and then this part is set what? Is set B, something like that. So what do? You shade everything here. This part which is blue, that's the A union B. You want all the elements which are in A and all the elements which are in B. Please do not repeat the elements which are on the intersection, right? You just write them once, something like that, because maybe you are given set as maybe as listed, something like that. So if you want to write them as listed, whatever, in that Builder notation that we've been talking about, then you need to make sure that you not repeat the elements which are at the intersection. Why? Because they will be both in A and in B, and you are taking them from the list, so you'll be attempt maybe to repeat that. Please do not repeat those. So that's the union there. So this was an example which says the union of the sets 1 3 5 and 1 2 3 is the set 1 2 3 5. Why? Because you are taking those elements here and those elements in this set, and then we join them, right, to make the union. And if you look at it, this 3, we didn't repeat 3 here. So this set union this set is just 1 2 3 5. Just take everything here, combine without repeating the elements. So the union of the set of all computer science majors at your school and the set of all mathematics majors at your school is the set of all students at your school who are majoring either in mathematics or in computer science or both, right? So let's talk about the intersection, right? This part. So if you are asked to shade the intersection, this is the part. We've got all the elements which are in A and B, right? So A intersect B is the set of all elements that are in both A and B, right? And they are denoted by this symbol that we have, this one. So it will be A intersection B or A intersect B. So an element X belongs to the intersection of the sets A and B if and only if X belongs to A and X belongs to B. Just like that. That is A intersection B. Is that X is an element of A and the X must be an element of B. So if you are being asked to shade intersection, this is where you shade, right? Then so the shaded region represents the intersection of A and B, right? Note that two sets are called disjoint if their intersection is the empty set. So you might have disjoint sets. So when do you have disjoint sets? It's when you have maybe set A and B, they do not have anything in common. Then we call it, these are disjoint set. They do not have this part of intersection. So maybe they will be like this in your Venn diagram. They will be like this. They will be not intersecting each other. So this will be disjoint sets, something like that. Then let's talk about the complement of a set. If you say A complement, we are talking of all the elements which are within the universal set or which are within the population that we are considering right at the moment. But those elements are not in A. Those are the elements that we say they makes up what we call A complement. So A complement or not A is the set of all elements in the universal set but not in A, denoted by this A bar, or it might be this power 1, something like that. Without this bar, it's still A complement, right? It's just a matter of which textbook are you using, something like that. So an element belongs to, also you can have this something written like this. I think it's good if I clarify here. Maybe A, some sort of to the power C, small letter C, is still A complement, right? So an element belongs to A bar or A complement if and only if X is not an element of A, but that element is still under the universal set. That's the very, very important point as well. So this shaded region will be A complement, or representing A is the area representing A complement. This one, the shaded region, this one is the one which is representing A complement. So for example here, let A is equal to this, which is a set of vowels, right? Where the universal set is the set of letters of the English alphabet, right? So A complement are all the letters, maybe those are the ones that you call consonant or something like that, which are not vowels, right? So we are talking about the English alphabet but not considering these vowels. So that will be a complement. Why? Because A is just this collection of vowels, something like that. So the complement operator is similar to the logical not and is reflexive. Something like if you say A bar bar, or the complement of A complement will be just equal to A, something like that. If you say the complement of A complement, we will get back to here, something like that. That's what you're talking about. And then there's what we call the set difference. The set difference, like A minus B, right? So the set difference A minus B is the set of elements that are in A with those that are in B subtracted out. So if you say A minus B, you are taking all the elements in A except those which are in B, which means you are taking out the intersection and only left with elements only in A, right? So if you are talking about B minus A, some kind of opposite, you are talking of all the elements only in B but not in A, something like that. So Another way of putting it is that you might find it as the set of elements that are in A but not in B. So it might be A minus B or A intersecting B complement, something like that. When you say A intersecting B complement, you end up having this, only this. Why? Because if you are supposed to shade the B complement is everything out of B, right? Everything out of B. But now we want things which are in A and out of B. Only those things are here, are in this part here, this part. That's why this part is the only shaded part. So A intersecting B complement is the same as A minus B, right? We call it the set difference. I think it's very, very simple there. And then there's what you call the symmetric difference. So these are just the basics, right? These are just the basics that you really need to understand. These are just the basics of sets, right? Of sets operations. Why understanding this? Because even when you are being asked to shade the wanted region, whatever, you'll be using these concepts, right? Like what we've done here, we have actually shaded A intersecting B complement here. Like I've demonstrated, how do you do it? First, look at A. The A is this part, whole party. Then what is B? This whole party, right? And now you want only A intersecting B complement. So what is B complement? So what is B complement? B complement are all the elements which are in the universal set, here or here, but outside of B, right? So we want things which are outside of this part of B. So we want all the things which are maybe those including in A, what, blah, 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 blah. And then because it's A intersecting B complement, now we want only elements which are in A and in B complement. What is B complement? We've said this whole party, right? And what is A? This whole part. So we only want this part, that's the intersection, this part, something like, so we shade this part, something like that. Okay, so let's talk about the symmetric difference. So given two sets, their symmetric difference is the set of elements that belong to either one or the other set, but not both. So when it comes to set difference, want those elements which are in A only and B only, but not. So you're just going to remove the intersection part, right? So that will be your set difference, that you just remove this part. You want only the elements which are in A and B, but not both. That's the set. So that's the symmetric difference. Okay, so there are these examples that you have here, and please, you need to go through these examples, solving these, whatever. These are basic. They look like kind of basic, but I think these are the things that sharpens you. So if you look at this, we've got this universal set with 1 2 3 4 5 6, and A is 1 2 3 and B is 3 4 5 6, right? Then you are being asked to find A intersecting B. So we want all the elements which are in A and B. So you'll go and look at A and B. So we have got 3 and 3. That's why A intersecting B are going to only have 3, because 1 2 are not part of B. Just like that. A union B want A elements which are in A or in B, something like that. So we are going to have 1 2 3 4 5 6, right? That's the union. Then B minus A, this is set difference. We want the elements which are only in B but not in A, something like that. So if you look at it, in A you've got 1 2 3, but here you've got 3 4 5 6 in B. So we are going to take out these 3 because we do not want things which are in A. We only want things which are in B, which is 4 5 6. So that's B minus A there. And then let's talk about what else? Let's talk about A minus B. Here now we want elements which are in A but not in B. So if you look at 1, yes, 1 is not in B, so we're going to take it. 2, yes, 2 is not in B, so we are supposed to take it again. Here there was supposed to be 2 here, it needs to be corrected there. And then 3, we cannot take it. Why? Because 3 is also in B. So we only want those which are in A but not in B. So 4 5 6, we are not going to take it, something like that. So here inside, you are supposed to have 1 2, and then B complement. B complement are the elements which are not in B but are also in the universal set. So here for 3, 4, 5, 6. So 1 and 2 are the only elements which are in the universal set but not in B. So we are going to have this. Then the set difference, the symmetric difference, A symmetric difference B. That's when we say that we remove the intersection. We only want those which are in A and in B, but not in both. So you just remove the intersection. So what was the intersection? It was 3. So you just remove 3 and you take. So you take 1, 2, and then you take 4, 5, 6. That's why we have this as asymmetric B. So that's how you solve this. So that's how you perform this set operation. So if there are any questions related to this, maybe that's the best time to come up with that. Otherwise, we've got these practical problems that we really need to solve. So if there are no hands here, what I will do is I will ask maybe you've got the A and the B as A is 1, 2, 3, 4, 5 and B is A, B, C, right? So we are being asked to find A minus B. What could be the answer here on C? If we say A minus B, someone to give me the answer there. Wilfred, if what Wilfred want to say something, you can admit yourself. A minus B. So the answer is what? Is 1, 2, 3, 4, 5. We want only the elements which are in A but not in B. So we want those which are only in A. And if you look at that, 1, 2, 3, 4, 5 is that, which is a good answer there. Maybe what do you say A intersecting B? Someone to give me the answer for A intersecting B. For A intersecting B. Davidson, you can just unmute yourself. Yes, the intersection is a null set or is an empty set. So you can also go on to do the cross product, like what we've said, matching this, whatever, 1A, 1B, 1C, 2A, 2B, 2C, something like that, when you're doing the cross product. So that's how you go around whatever. That's how you perform these set operations. So let A be the set of students who live within 1 mile of school, and let B be the set of students who walk to classes. Describe the sets in each of these sets. So sometimes you might be given, like what I've said, there are ways of represent a set, right? So here you are being given a description. So what could be A intersecting B here? How do you tell that A intersecting B? Or how do you give the description of A intersecting B? You are being told that let A be the students of who live within 1 mile of school, and those in set B who are going to be students who walk to classes. So what does A intersecting B mean? Right? How do you say this? How do you say that? Not you afraid? Do I have any new hand? I only have you afraid. I only have the Devson. No, not Devson. Oh, Sandra. Yes, Sandra, you can try. So what are these students in both A and B? Exactly. So these students live 1 mile within 1 mile of school, and they do walk to classes. That's A intersecting B, something like that. Okay, so that's how do you do this. Then you'll be asked to draw Venn diagrams representing this whatever. Draw the Venn diagram diagrams for each of these combination of the sets A, B, and C. So maybe you need to draw the Venn diagram, and then after drawing the Venn diagram, you put A, B, and C there, and then you are required to shade A intersecting B union C, and A minus B union A minus C union B minus C. So when it comes to these things, what you really need to do is, if you look at what we did here, this is like what when I was explaining here, that's what you really need to look at, right? So if you come to this scenario, it's only that I do not have a pen that I can use to draw smoothly, but let's have this something like this. Let's try the first one. Sorry, I'm using the mouse there, not the mouses, but I'm using. Okay, so this will be A, this will be B, right? This will be C, this one. So you'll be asked to draw A intersecting B union C. So what you really need to understand is you want the set A and the elements which are in B union C. Is that making sense? You want those things which are common in A and B union C. So what are these elements, right? What are these elements? So let's look at the very simple scenario that we can look at here. So those which are B union C, what is B union C? The elements which are in both B, not both, but which are, we are taking B or C, something like that. So we are going to take all the elements which are in B, right, and those which are in C. So this is C, right? This is what we want, right? This is what you call the B union C. So this is the elements which are in what? Which are in both, not both, but which are in B or C. That's the union. So now we want those which are in A. So can you make sure that we are all on mute? All right. So now we want those which are in A as well as in this part that we have already shaded. So if you look at that, those members, excuse me, let me just switch to maybe to red. So those members, so this is the set A, right? So all the things in A are in here, in here, in here, in here, but the already shaded part is this part, right? So we want this is the region that we are going to shade, right? So this is the part that we are supposed to shade, because this is the part that we want. So we want things which are in A and in both B and C, something like that. So we want this part, this intersection, something like that. That's what we want, this part only. So we are going to leave things which are in B only and things which are in C only, and then we take those things which are in both B, C, and A, something like that. So we are going to take this. So that's how you do this. So for this one, you also need to find the set difference of B, the set difference of A and C, and then you find the union, right? So it's some sort of trying to find a way of how do I do this step by step. What is A minus B? These are things in A only. Then you want the union of things which are in A only, not in C, and you want things which are in B only, not in C. So it's a union. So you are just joining those things, then you shade that part, or you just list those elements. Maybe here just here you perform shading. Why? Because sometimes you'll be required to do shading, but mostly here you are just listing those elements, so that way it will be easier to really do that. So that's all on sets. I don't know if there are any questions on sets. Otherwise, that's everything that I really wanted to cover, and that's everything which is very important for you on this one. So if there is anything that you need on set theory, please, this is the time to ask. Otherwise, we are going to talk about what we call relations. This is what we call relations in a mathematical foundation, right? So normally when you're doing mathematical foundation, some of the things you see them when you're doing discrete mathematics. So mathematical foundation is part of discrete mathematics, or is just an introduction to discrete mathematics, right? So please take it seriously. Why? Because when you're doing discrete mathematics, some of the things that you'll be applying there are the things that you have learned in here, right? So let's look at what we call relations. Let's look at what we call relations. All right. So by the end of this unit, you should be able to describe the concept of relation between two sets, use the appropriate methods for representing relations, explain some of the properties of relations. So normally when you're talking of relations, there's this definition which says let X and Y be two sets, right? And I will call it maybe A be a binary set. So a relation R, so a relation R, sorry, from X to Y is a subset of the Cartesian product X cross Y. So when you are looking of a relation, guys, we are talking of a subset of a Cartesian product. Cartesian product is the one that we have done when we are saying that if you are given set A and set B, you say A cross something, whatever, when we're saying 1 1 or whatever, 1 2, something like that, when we're crossing those elements, right? So we take a subset of that Cartesian product, right? And remember, when you're doing the Cartesian product, we would have a set with a sum within maybe some sets like this, right? Maybe I could have this as well so that it will be easier. So when you're doing relations, you are building on this, right? On this part, where we are talking of power sets, right? This Cartesian product, right? So if you look at the Cartesian product, now a relation, it will be a subset of this. So maybe you might take this part 1 2 3 maybe as our relation. Why? Because that will be the one which is satisfying the condition that will be given for that relation. So a relation, it will be a subset of this Cartesian product that we do among the sets. So we might say A cross B, and then want the relation which suits that. Maybe what we say, maybe the first element, or X must be equal to 1, which means we take only those with 1 here, right? So you take 1A 1B 1C, something like that, then this will be our relation. So that's what we'll be working on, something like that. So that's what we call a what? A relation there, right? So this one was just another definition of that. So if X is a set, so this one just an example which says if X is a set of students X, which is equals to Jim, Sheila, Shamiz, Rai, and Y is a set of courses X, courses Y, sorry, computer science, math, then maths, then art, then history. So a relation R between X, Y, indicating courses taken by the students, can be written as, so here we'll be having this relation, right? Which says that Jim is doing this, whatever, Sheila is doing this, Sham is doing this, something like that. That will be, so if you look at it, we are crossing, right? We are making a cross, and then we are only and then we are taking things which suits the relationship that we want, right? Like here, if you are going to do the cross product, we just cross Jim with all computer science, math, art, history, Sheila with everything. But here we are saying no, Jim is not doing everything, right? So what is Jim doing? Now there's now a relationship, or a special relationship that we are using, and that one is the one that which defines, or which makes a relation. So here, if you look at this, we have got Jim computer science, which means Jim is doing computer science, and Sheila math, which means Sheila is doing mathematics, something like that. Jim art, which means Jim is doing art, something like that. And Shami history, also Shami is doing history, Shami is doing computer science, Rai is doing math. So since Shami then history is an element of R. We may write Shami R history. So normally you could see this notation as well, to which represent relation like this. What does it mean? It means that Shami is related to history, which means Shami is doing history, something like that. So you might find A related to B or X related to Y, something like that. So that notation just means that this element from the domain, whatever, is related to this, whatever, from the what do you go from the range, whatever. We are going to talk about that when we talk about functions. So we can represent a relation in above example pictorially by using an arrow diagram. This arrow diagram where you could have X and Y there, which is these students and courses. So this will be students, then courses, and then we can use the arrow diagram to point that Jim is doing computer science and doing art. Sheila is doing math, maybe math only. Then Shami is doing computer science and history. Surah is doing math only, something like that, right? So here is an example to which says, suppose X is equals to 2, 3, 4 and Y is equals to 3, 4, 5, 6, 7. If we define a relation from X to Y by XY is an element of R, if X divides Y, so if X can get into Y, giving remainder 0, something like that. So what could be that relation R? So if you look at it, we have said that the relation R, instead of this, I think I do not need it. Let me look for, I need a highlighter, not a pen, right? So if you look at it, we have agreed that the relation, it will be a subset of the Cartesian product, or that cross product that we have been doing. So the cross product, we're supposed to have 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7. Then if 4, 3, 4, 4, 4, 5, 4, 6, 4, 7. So that was going to be the entire Cartesian product. But now we have got this special relationship which makes our relation R that we want. So we are going to take these things or these subsets whenever X divides Y. That's why we see that here our X is 2, our Y is 4. Why have we take this to be part of our relation? Why? Because we can divide this 4 by 2 and getting a remainder 0. Or X divides Y. Here we have got 2, 6. Here we've got 3, 3. Here we've got 3, 6. Here we've got 4, 4. Why don't we have 3, 5? Because 3 cannot divide 5. Just like that. And we can have its pictorial representation just like this. 2 linked to this 4 and to 6. 3 linked to 3. And then 3 linked to 6. Something like that. 4 linked to 4. Just like that, right? So this was just an exercise which says, suppose that we've got X, Y there. Write a relation R between set X and set Y defined by XY is an element of R if X is less than Y. So if you are doing this, now you are looking at maybe 1, 3, 1, 6, 1, 9, then something like that. That whole set, then you only take those where you have X will be less than Y, which means 1, 3 is acceptable, 1, 6 is acceptable, 1, 9 is acceptable, 2, 3 is acceptable, 2, 6 is acceptable, 2, 9 is acceptable. Why? Because this value will be less than whatever the value that I pick of Y. But 3, 3 is not acceptable. Why? Because 3 is not less than 3. Just like that. So 3, 3 will be out of that relation. So you do not put it when you're writing like what you're doing here. So you do not need to find this 3, 3. And then 3, 6 is fine, 3, 9 is fine, 4, 3 no, because 4 is not less than 3, 4, 6 is fine, 4, 9 is fine, 5, 3 no, we do not want it, 5, 6 is fine, 5, 9 is fine. So you can also do the same where you say Y is equals to X. So whatever, Y must be twice the value of X, something like that. So that's what you do there. Then the inverse of a relation, let R be a relation from X to Y. So the inverse of R, which is denoted by R to the power minus 1, is the relation from Y to X. So it's now like some sort of a reverse. Now we are talking of a relation which will be from Y to X rather than from X to Y. So if we define a relation R from X to Y by X, Y is an element of R if X divides Y, we obtain this, right? This is what we This is what we obtain. So the relation can be represented pictorially as this part 2 4 whatever, then whatever linked like that. But now when it is an inverse, now what does it do now? Then you need to know that what was your x will become your y, whatever, something like that. So this will become your x, this will become your y. So you now interchange where you were having this 2 4, it's now a 4 2, just like that. So that will be the inverse of that relation. And then there's what you call the composition of relations. I think this is also the thing that you really need to understand. This will also go to the function composition, something like that. It will be some sort of that thing, right? How do we come up with this? Now there is this introduction. If you look at the relation that we've been talking about, it was a binary relation. We talk about ay, xy, something like that. And then on this one now we've got x, y, z. So we've got x, y, z. So a composition of relations is when we try to link this part and this part through this y, right? That's what we call the composition of relations. So let R1 be a relation from x to y and R2 be a relation from y to z. So you'll be having a relation, maybe R1 which will be linking x and y, and then we have got R2 which will be linking y and z, something like that. So if you want to combine those relations by R2 dot or this some sort of or kind whatever R1, so is the relation from x to z defined by this R2 dot R1, and then xz is such that xy is an element of R1 and yz to be an element of R2 for some, y is an element of y. Like what we have here, this diagram which shows that you'll be having this linked to this, then linked to this. So we want to link this x and z through this y. I think we'll talk about this when I talk about some special types whatever of relations. So let's look at this example which shows this composition of relations. So suppose we've got these two relations, R1 that will form here and R2 that will form here. Then from this definition, if you want to find the composition of these relations, you can draw the pictorial representation of it. If you look at it, we've got 1 2 on R1 which is going to be 1 2, then 1 6 which is both on R1 we've got xy, and then on R2 if you look at it we'll be having xz there. So here we've got 1 6, we've got 2 4, that's 2 4, whatever 3 4, you put 3 4, whatever 3 6, you put 3 6, 3 8, you put 3 8, and then for R2 you'll be having now 2u whatever 4s, then 4t, and then 6t, and then 8u, something like this. So this is what we have. So what if you want to find the composition of R2 and R1? How do you do that? If you look at it, now we have our new xy there, where y is now this is z, right? And x will remain this part. So how have we eliminated this? How have we eliminated this? If you look at that, now we've got 1u. Why do we have 1u? If you come here, you can go from 1 here up to u. So this x is linked with the z through this 2. So it will be 1u there. And then find that we have 1t. Why 1t from 1 to t? If you look at it, we've got from 1 there. You can go here, you can go to t, whatever, 1 here, go to t, something like that. And then we've got 2s. Why 2s? From 2 here, you can go straight to s. So 2 is linked to s, something like so. That's how we end up having this, the combination of r in relation R2 and R1, something like that. That's how we ended up having that, right? So now let's talk about the important relation on a set, the types of relation on a set, right? we've got what we call the reflexive relation. We've got what we call the symmetric relation. We have what we call the antisymmetric relation, and we've got what we call the transitive relation. So you need to know the rules or what makes this relation to be a reflexive relation, what makes this relation to be a symmetric relation, what makes this relation to be an antisymmetric relation, what makes this relation to be a transitive relation, something like that. So these are some of the things that you really need to know, right? So now let's look at the definition of these relations on a set. So a binary relation R on a set X is a relation from a set X to a set X, like this one. We call it so relation on a set, right? So this is a relation on a set. If you have a set A, so this will be a relation on set A itself. So if you have set X, this will be a relation on set X itself. So it's now different from these relations that we have been talking about of having maybe set A and set B, something like that. Then we do the cross product of those set A and B, then we take the subset of it, and then we make a relation. So here we are just taking the set itself, and then we cross the set with itself, and then we take the subset of it to make a relation that we want. So for example, here we have got let R be the set be the relation on set X. What does it mean? So this set X will be 1 2 3 4 5 defined by X. Y is an element of R if X is less than or equal to Y. So xy will be the element of x. Why xy will be the element of x? Because x will be crossed with x. So the values that we're supposed to get here for x and y all will be belonging to this set x. And here we want the values where x is less than or equal to y, which means we are going to have another set, maybe x here, which will be having 1 2 maybe 3, then 4, then 5. Bear with me, like what I said, I do not have a pen to write. My computer is not a touch screen, so I could not just write. So this is just a curly bracket, this one. Maybe if it was whatever, I could just write with a pen or with a finger there. It was going to be easy. So we'll be crossing like 1 1 1 2 1 3 1 4 1 5. Then we do 2 1 2. Then we only take those with this relationship. So the relationship was x must be less than or equal to y, right? Which means we will be saying is 1 less than or equal to 1? Yes. So you're going to take 1. 1 less than or equal to 2? Yes. So we take 1 2. We take 1 3, we take 1 4, we take 1 5, we take the next thing close 2 with everything there. So it's 2 less than or equal to 1, no, so you do not take 2 1, but 2 2 you can take, 2 3 you can take, something like that. So that's why we end up having this relation here. So this will be our relation. I think it makes sense if you look at that. So let's now talk about the reflexive relation, what we call a reflexive relation. So a relation R on a set X is called reflexive if x or if this party and this party are element of R for every x is an element of X. So in short, a relation R on set A is called reflexive if AA is an element of R for every element A is an element of A. So in short, this is what defines a reflexive relation. So whenever you have a set like this, we must have every element mapped to itself for it to be a reflexive relation. So it might have any something else, whatever it can have, but every element of this set must be mapped to itself for it to become a what? For it to become a reflexive relation. I hope it's making sense there. I hope it's making sense there. Right? So here it was saying the example was saying that the relation r on x 1 2 3 4 for the example as shown in the previous slide above is reflexive because for each element x and m. Let's look at it. What do we have here? Maybe you are explaining the example which was here, this one. Okay, we are saying this one, it was a reflexive relation. Why? Because we've got 1 1, we've got 2 2, must have a 3 3 as well, we must have a 4 4, we must have a 5 5. So we call it a reflexive relation. Why? Because inside this relation we also have all the elements mapped to themselves, something like that. So it was saying that this example, it was just saying this set that we have here, this relation is also a reflexive relation. Now let's look at example. Let's look at example 2. Consider the following relations on this set, right? We've got this set 1 2 3 4, and we've got the relation r1 r2 r3 r4 r5 r6. So you might be asked, which ones are reflexive relations and why, and which ones are not reflexive relations and why, right? So if you look at the first one, you need now we are given that these relations were formed from this set 1 2 3 4, right? So you, what do you look for? You look for every relation that have got every element mapped to itself, right? If that condition satisfies, then it only tells you that the relation is reflexive, just like that, as simple as that, right? So like here we have got 1 1. Do we have a 2 2? Yes. Do we have a 4 4? Yes. What is, where's the 3 3? We do not have. So R1 doesn't qualify to be a reflexive relation, just as simple as that. Now let's look at R2. R2 have got 1 1, doesn't qualify to be a relation because we do not have a 2 2, we do not have a 3 3, we do not have a 4 4. So it doesn't really qualify to be a reflexive relation. So, and then R3, do we have a 1 1? Yes. Do we have a 2 2? Yes. Do we have a 3 3? Yes. Do we have a 4 4? Yes. So once we have that condition fulfilled, then it means that this R3 is a what? Is a relation. Then it's a reflexive relation. So what else is a reflexive relation here? What else is a reflexive relation? We've done from R1 to R3. I need a hand. Someone to try. Sandra, no. I've got Mpof. Emsley. Mpof. You can unmute yourself and then tell us which ones. I know the answer is there, but I want you to tell us which ones reflexive relations and why, and why you say this one is not a reflexive relation. You can unmute yourself. Exactly. Thank you for that. That's all what you need. If you're being asked to identify from all these relations which are reflexive relations and which are not, that's what you only need to mention, right? R1 is a reflexive relation because of this, but here it's not. So R1 is not a reflexive relation. Why? Because here 3 3 is not mapped to itself, or 3 related to 3 is not the element of our relation. So no go to number 3 related to 3, so to 3 is not. These are some of the resources which are very, very important. So you say it's not like this, is not an element of what? Of R1. This one you write R1, something like that. So because 3 3 is 3 related to 3, or 3 3, something like that, you can write like this: 3 3 whatever is not part of relation 1 or of relation R1. So it means this is not a reflective relation. So you go here, you identify that 2 2 3 3 4 4 is not part of this, so it is not a reflexive relation. You go on to whatever, something like that. This one is a reflexive relation. Why? Because 1 1 2 2 3 3 4 4 are part of this, something like that. So that's what you do there. That's what you do there. So I'm seeing that on YouTube those others are coming. R5 the elements x related to itself. Yes, that's it. That's it. Okay, so that's how you go about this. Now let's look at what you call a symmetric relation. So it's just a matter of mastering, right? You just need to master. What does the definition say of a symmetric relation? After you master that, then you do not have any challenge, right? Just like that. That's what you need to do. So let's look at this definition, which says that a relation R on set X is called to be symmetric if for all x, y are element of X, if x, y is an element of R, then yx must be also the element of R. So in short, we are saying whenever we have x is an element of y, we must also have y being an element of x for it to be a symmetric relation. So whenever y is an image of x, we must also have x as the image of y for it to be a reflexive relation, just like that. I think it makes sense and very, very clear as it is, right? So R is not symmetric if and only if this IFF is if and only if there are elements A and B such that the elements A and B in A such that AB is an element of R but BA is not an element of R. So whenever you have got an element AB and you do not have a BA, that relation automatically will now not become a symmetric relation, just like that, right? That's what it means. So for this example, consider the relation R on X is equals to A, B, C, D given as follows. R is equals to, we've got A, D, B, C, C, B, D, A. Is this relation a what? A symmetric relation. So you look here for, if you have an AD, look for DA. We have it. If you have a BC, look for CB. So we have it. So it means that this relation that we have here is a what? Is a symmetric relation. Why? Because for all x and y that we have, whenever x, y is an element of R, we also have y, x as an element of R. So in this case, we have DA, CB, BC, and AD are all in what? Are all in R. Hence, R is what? Is a symmetric relation. Just like that. Right? So that's what it is there. So there is this example where we are supposed to pick which ones are symmetric relations and which ones are not, right? So let A be 1, 2, 3, 4 and define relations R1, R2, R3, and R4 on A as follows. R1 is 1, 1, 1, 3, 2, 4, 3, 1, 4, 2, 1, 1, 2, 2, 3, 3, 4, 4, something like that. And this R3 and this R4. So which ones are symmetric and which ones are not symmetric? Remember, we've said that whenever you have, like you have got 1 1, right? This one, whenever if 1 1, it's already 1 1 is already mapped to 1 1, so you don't need to look for another 1 1, right? And then when you have a 1 3, you need to look for 3 1. So we have this and we have this. Good. Then when you have a 2 4, now we need to look for a 4 2. Then we have this 4 2, which means that R1 is a symmetric relation. Why? Because for every ordered pairs AB in R1, we also have BA in R1. Just like that. Let's look for R2. R2 also is a symmetric relation. Why so? Because we've got a 1 1, we do not need to look for another 1 1 because we already have a 1 1, right? So it will be a repetition. 2 2, 3 3, 4 4. So the what do you call it? Now the rules for symmetric relation have been met. So this will be also a what? A symmetric relation. Take note of that. Okay. So this one, it will be both reflexive and symmetric, right? You need to know that. So now let's look at this one. We've got 2 2, you've got 2 3, and we've got a 3 4. So whenever you have a 2 3, you need to have a 3 2. So we do not have that 3 2, which means R3 will be disqualified as a symmetric relation. What about R4? What about R4? Someone to comment. What about R4? Someone to comment. I need someone to comment. Tell me about R4. Is it a reflexive relation or not? I have Tanaka there. Tanaka Mzirwa, you can unmute yourself. Let's talk about R4. Let's look at this. Yes, that's it. Because we've got a 4 3, we must have a 3 4. So this disqualifies R4 as a symmetric relation. So basically, that's how you look at these things. That's how you look at these things. It's not that hard to do, but I don't know what happens when people are alone, right? So now let's look at the antisymmetric relation. When it comes to this, I always laugh. Why? Because sometimes when you read symmetric and then symmetric, you think that this is the opposite of symmetric. That's what it is not. That's what it's not what you think, right? So a relation R on a set X is called antisymmetric if for all x, y and are element of X, when x, y is an element of R and X is not equal to Y, like those what, something like that, and X is not equal to Y and YX is not an element of R. So this is two mathematical definition. Maybe when you are doing something, the one on which was saying R4 is not symmetric. Okay, for that one, I think that's correct. Okay, so let's look at these remarks are the ones which can try to make it clear to us what are we talking about when we talk about antisymmetric. So R is not antisymmetric if and only if there are elements A and B in A such that A, B is an element of R and B, A is an element of R, but A is not equal to B. So if you see that, you know that R is not antisymmetric, or that relation is not antisymmetric. Whenever you have A, B, and then you have B, A, where this A and B are not equal, like the 1 1 2 2 that we used to get, whenever you see that, that's what we used to say about a symmetric relation. So it means that that thing is not antisymmetric, something like that. That's what we are talking about. Okay, so the second thing is that the properties of being symmetric and being antisymmetric are not negative of each other. It's not the opposite of each other, right? So let's look at this example. Maybe this will help us to clearly explain what are those relations that we said this is antisymmetric. So consider the relation R on X, which is ABCD, which is given as follows: AB, BC, CD. So we've got AB, we've got a BC, we've got a CD. So the relation is antisymmetric because for all xy, when xy is an element of R and x is not equal to y, also y, x was not an element of R. So if you look at it, we are saying whenever we've got an AB where this value of A and value of B are not the same, right? If you look at it, we also do not have a BA. When you have a BC, we do not have a CB here. When you have a CD, we do not have a what? We do not have a DC. So this makes this relation an antisymmetric, right? I hope we now start to make some sense out of it. So when you're doing these examples, maybe it will tell us, right, what does it mean when you say antisymmetric, right? So now let's look at let A be equal to 1, 2, 3, 4 and define the relations on A. R1 is 1, 1, 2, 2, 3, 3. Then we've got 1, 2, 2, 2, 2, 3, 3, 4, 4, 1. And then we've got this, we've got this. So let's talk about which one is antisymmetric and which one is not, right? If you look at this, we're saying whenever you have AB, when A and the values of A and B are not equal. So there's this exception of being not equal, which means if they're equal, we ignore. So if you look at this, we've got 1, 1, a 2, 2, and a 3, 3. It means this one is symmetric, right? Yes, it's symmetric because we are saying that if it is for a symmetric one, whenever I've got 1, 1, we must also have a 1, 1. And we've said that if you have a 1, 1, it's automatically the other 1, 1 is already there. We do not repeat 2, 2, 3, 3. For antisymmetric, we have said that whenever if you have AB, you must not have BA if those values of A and B are not equal. But if they're equal, there's no problem. So we can have 1, 1, we can have 2, 2, we can have 3, 3. So it means this one is both antisymmetric and symmetric. That's why we say that the definition of being antisymmetric and being symmetric is not negative of each other, right? Now let's look at R2, right? On R2, we've got a 1, 2 there. Fine, no problem. And whenever I have a 1, 2, because this A and B are not equal, we must not have a 2, 1, right? Or we must not have a BA, something like that. We have a 2, 2, fine. We've got a what? A 2, 3, fine, because we do not have and we've got a 3, 4, fine. And we've got a 4, 1, fine. So what does this mean? It means this R2 is also antisymmetric. Why? Because whenever I have 1, 2, because this and this are not the same, right? So whenever I have 1, 2, we do not have a 2, 1. Whenever a 2, 2, it's fine because these are equal, we can have a 2, 2. 2, 3, we do not have a 3, 2. 3, 4, we do not have a 4, 3. 4, 1, we do not have a 1, 4. Something like that. So this means that this one, it's antisymmetric. And also it is not symmetric. Why? Because when you have 1, 2 in R2, 2, 1 is also not part of it, something like that. But for now, let's look at the issue of antisymmetric. So this one is antisymmetric. Then let's look at R3. When we are looking at R3, we have got 1, 3, right? We must not have a 3, 1. So automatically this is now antisymmetric. So what about R4? What about R4? Is R4 antisymmetric? Someone to explain, is R4 antisymmetric? Just you want new hands, not Wilfred. Wilfred, someone. New hand. Blessed Clay, are you there? Blessed, are you there? Can you give it a try? Okay, your mic, maybe your mic is not working. Maybe I'll try. Chipomanika. Are you there? You can give it a try. Who else? Malvin. You can unmute yourself and give it a try. Do you want to try? Okay. Let's talk about R4. Is it antisymmetric? Is it R4 antisymmetric? This one? Why are you saying it's antisymmetric?
We have P1, 2, 4. We don't have 4, 3, and for 4, 3 we don't have, and 1, 3, and 3. So it cannot be antisymmetric.
Okay. The answer is you have mixed it up. Some have mixed up. You've started by saying R4 is antisymmetric and then went on to say it's not antisymmetric. But thank you for your contribution. At the end, R4 is not antisymmetric. That's true there. Why? Because when you're looking at the issue of antisymmetric, we look at what we are considering. First, we need to have these as not equal, right? So if they are not equal, then when you ever see that this one and this one is not equal, you must not see that pair reversed, something like that, within that relation. So whenever I see 1 3 and then see a 3 1, know that that one is no longer an antisymmetric relation. So this one is not an antisymmetric relation. Why? Because we've got a 1 3 and we've got a 3 1, just like that. So that's what it is. Okay, so let's look at what we call a transitive relation. So the transitive relation, maybe it benefits from what we were talking about when we were talking about the composition of our relations. Maybe we can just make sure that now we are all muted. Okay, Tanaka, you can lower your hand there. Okay. So this one benefits from that. Why? Because it's a question. Okay. Yes, let's. Mhm. No. Okay. Just to finish your question. Okay, maybe you've missed it on that. You've missed it on that. What we are saying is, when you are looking at the qualification of it being an antisymmetric, right? It ignores the issue of being equal. So what happens is, like if you see here, Parunzi, R4 is neither antisymmetric because 1 3 and 3 1 are element of R4, but 1 and 3 are not equal. So what it means is that when you have a 1 1 there, this part and this part are equal, or x and y are equal, right? So whenever they are equal, we can have them being repeated. We can have them being one, another one again, something like that. But because whenever you write sets, you do not repeat elements, something like that. So whenever you have a 1 1, a 2 2, a 3 3, a 5 5, whatever, automatically that thing become an antisymmetric relation. But when now you have something different, like on x and y are not equal, then we must not have those elements now being reversed. Something like, yes, something like here. So in here we can have a 1 1, a 2 2, a 3 3. But whenever we will have now a 1 3, you must not have a 3 1 for it to be antisymmetric. Is that making sense? So if you look again here, we've got a 1 2, and if you look at, whenever you have a 1 2, we do not have a 2 1 here. Here we have a 2 2, and we have accepted it. We have a 2 3, and we do not have a 3 2 in here. We've got a 3 4, and you do not have a 4 3. We have a 4 1, and do not have a 1 4. So this makes this one an antisymmetric relation. So whenever you are looking for an antisymmetric relation, whenever you see the element here being repeated like 2 2 3 3, whatever, where x is equal to y, a is equal to b, something like that, ignore that. Automatically it qualifies for antisymmetric. But whenever you have this and this not equal, stop there, check, does the whole set do not have these two numbers now reversed, something like that. So whenever you want to stop there, check, don't we have a 2 1 in here? No, we do not. Whenever you have a 2 2, skip it. Whenever you have a 2 3, stop there. Why? Because these two are not equal. Then check, don't we have a 3 2 in here? We do not have. Then it's okay. Do we have a we have a 3 4, stop there, because these are what? These are not equal. Check, don't we have a 4 3, something like that. That's how you check for antisymmetric. Yes, and there's a special meaning for that. We'll talk about it later. Yeah. Okay. Okay, thanks. So now let's look at what we call transitive relation. So a relation R on a set X is called transitive if for all X, Y, Z are elements of X, when X, Y, Y, Z are elements of R, then X, Z is an element of R. This is a little bit too long and too mathematical. Let's look at how best can we make this simple. But like what I've said, it borrows from that idea of relational composition, where we would have X, Y, Z, and we're saying that, sorry, X is linked to Z through Y, something like that. So we are going to have sets relation from X to Z be linked through Y, something like that. That's the transitive relation there. So let's look at this. Consider the relation R on X, A, B, C, D, which is given as A, B, A, D, A, C, B, C, B, D, C, D. Is this relation a transitive relation? Yes. Why? So whenever you have an A, B there, let's look at this. Okay, let's look. So yeah, they are saying that, for example, here we've got A, B, right, which is an element of this R, and we've got BC, which is an element of R, this one, and we've got AC. If you look at it, sorry, I've said that. Okay, so if you look at it, you have AB, you have BC, and then you have AC. So if you look at it, AB, BC, then AC. So A is linked to B and B is linked to C. Whenever you have such thing, then A must be also linked to C, something like that. So A must be also linked to what? To C, or A is related to C through this relationship of B. A is related to B and B is related to C. It means that somewhere A is also related to C. That's what I was saying. So there is this B which is working as a hotspot, something like that. Yeah, but that's not it, but something like that, right? So that's the function composition that we're talking about, where you have got x, y, z. So x is now related to z through y. So a is related to b is related to c. It means that a must be also related to c. So you look for those things. Whenever you have a, b, b, c, you must also have a, c. Just like that. Whenever you have that, then it becomes a transitive relation. As simple as that. So you identify like that. Here we've got a, b. Do we have a something? Or do we have b something? So if you have a, b, you look for b something. Whenever you've got b, c, now look for AC. Do you have AC? Yes. Right? Do it for the other. Here we have AD. Do you have D something? No, we do not have D something, right? So there's no need of checking it. But here we also BD, right? We have what? We've got BD. What else do we have here? So if you have AB and B is linked to D, it means A must be also related to D. That's why we've got this AD, which is good. And then here with CD, we have what? CD. What do we need with this CD? Maybe I'm just using the same color there, so I think it's good if I change the colors there. But if we have CD, do we have something linked to C, B, C? No, not we've got a B, C, and then what we A, we've got AD, this one. We've got AC, then CD, which means A is related to D. Okay, so which means I have already talked. Okay, so I was already talked about this. Okay, maybe the issue of using the same color there, I need to use the. Okay, let's look for. We do not have many examples on this one, so I think you need to look for many examples on this. But basically, that's what we call a transitive relation. I don't know if I really need to explain more on this. Maybe we can try to relook at it. Otherwise, that's the um that's the transitive relation. Maybe we really need to relook at this. Let's try to go again. We've said that whenever you have AB, right, there's no problem. What you need to do is you need to look at, is B linked to something else? If B is linked to something else, it means A must be linked to that through B, something like that. So if we have AB, look for B something, right? Which means we've got a BC here, right? So whenever you have a B something, it means A must be linked to that. Also, we've got a BD here, which means A must be also linked to what? To that. What else? So for this, so you have AB and the B is linked to C. So you must also have AC. Now you look for those things, right? Now you look for those things. So I just need to change to a red color. So we have got AB and a BC. So we must also have AC, and we have it here. Sorry. We must we're talking about the AC. So we have this AC, and then because we've got BD here, so A must be also linked to D. So that's why we have this AD here. And then what else do we have here? We have AB and a BC, right? Yes, this is the thing that we have. What else do we have? I think that's all. What else do we have? We've got AC and CD, AC and CD. So we must have AD, this one as well. So that's all on transitive relation. You can go and find more examples to do on this one. Then I think things will be will be easier for you, but that's the transitive relation. And then maybe we'd want to talk about a digraph, and unless if there are questions or contributions, but if there are no questions or contributions, let's look at what we call a digraph. This is another very, very important thing that you need to take seriously. Why? Because you might be asked to draw a digraph. You need to know what is a digraph, how do you draw a digraph. So you might have these all relations that we've been talking about, all these relations, but you must be able to take these relations and represent them in a form of a what? In a form of a digraph. It's that simple. So one way to picture a relation on a set is to draw its digraph. So a directed graph or a digraph consists of two finite sets, which is a set VG, which is a set of vertices, and a set DG, which are directed edges, right? So you have edges and vertices, something like that, where each edge is associated with an ordered pair of vertices called its endpoints. So if edge is E is associated with the pair VW or vertices, what do you do there? Then E is said to be the direct edge from V to W. So you write or you draw an edge from V to what? To W, and is represented by drawing an arrow from V to W. So normally this is an example of a digraph, right? So here if you look at it, we've got a V1, V2, V3, V4. What else? So yeah, we'll put V1, V2, V3, V4 as vertices, right? So if you look at it, this E1, this edge E1 is a loop. It means we've got V1, V1, something like that, related to each other. So it will be a self loop, like a 2, 2. It will be a self loop at that vertex, something like that. So this E2 that we have, it means that we've got V3, V1, something like that. There's a link between that. So here this V3, V1, something like that. So you draw a line with an arrow there. And then because there's this going back here, which means we've got V3, V1 as well as V1, V3, something like that. It's some sort of where you have got 2, 1 and a 1, 2. So you draw the line, go there, and the line going back, something like this. Normally, that's how you represent all those things on a what? On a digraph. Here we've got a V3, V4, and also a V4, V3, something like that. And this one is just I don't know why is it bi-direction or whatever, but it was supposed to be or to have an arrow there which says we are going this direction or something like that. So basically that's how you draw a digraph. If you have maybe something like this, you want to draw a digraph this, what you need to do is to first put the vertices. What are the vertices? Are 1, 2, 3. That's the vertex. So you've got V1, V2, V3, or just one, maybe a 2 there and a 3. So if you want to put this on a digraph, you have a 1, 1, so it will be a self loop. So you put a self loop there. Sorry. And then here 2, 2, you put a self loop. And here you put a what? You put a self loop. Also, you might be asked to comment by just looking at this drawing. It could tell you that what is this? It could tell you that this is a reflexive relation. Why? Because at each and every vertex we have got a self loop there, something like that. I think you will talk about that later, but that's how you draw the digraph for this relation. If it is for this, the vertex that we have is 1, 2, 3, 4. 1, 2, 3, 4. You put 1, 2, 3, 4, and then you put a line from 1 to 2, and then a self loop at 2, 2, at 2. So you put a self loop. Then you need to draw a line from 2 to 3, another line from 3 to 4, and another line from 4 to 1, something like that. So sometimes you might be required to comment by just looking at a digraph, right? So how do you comment? You normally use the characteristics of a relation and a digraph. So we determine the characteristics of a relation by using digraph. So reflexive relation has a loop at every vertex. That's why I said this one's a reflexive relation by looking at its digraph. Why? Because it have got a self loop right at each and every what vertex. Then a symmetric relation has the property that whenever there is a directed edge from V to W, there is also a directed edge from W to V. Remember, when we talk about the symmetric relation, we are saying whenever you have an AB, you must also have a BA when A is not equal to B. So it's obvious that on this diagram, we must maybe when I talk of this, we must have maybe something going here and something going back in reverse, something going here and something going back in reverse, something like that. So whenever there is a one link from here to here, we must also have a link going here. So that one qualifies it for what? For a reflexive relation. Not reflexive, sorry, for symmetric relation. So those are the things that you will be looking at. So whenever there's an arrow from V to W, there must be an arrow going back from W to V. So V to W, then W to V. That one will become automatically a symmetric relation. So that's what we'll be looking at. And then antisymmetric relation has the property that between any two vertices, there is at most one directed edge. There must be at most one directed edge. So we must not have more than one directed edge. That's what it means on two vertices. On two vertices. So, and then for transitive relation, if you have A, B, and B, C, A must be also linked to C. So whenever you have an arrow from A to B and B to C, you must also have another arrow from A straight to C. So it's the fact that whenever there are directed edges from X to Y and from Y to Z, there is also a direct edge from X to Z. So from all these characteristics, we can now see that by looking at a diagram, we can determine, is this relation a reflexive? Is this relation asymmetric? Is this relation antisymmetric? Is this something like that? You can look at it by, you can see it by just looking at that. Then there is what we call partial order, and you might be asked to prove if yes. Okay. Mm-hmm. When you're drawing those loops, are you left-handed or right-handed? Are you left-handed or right-handed? Because normally we tend to draw the circle going one direction mostly. Yes. So my answer there, let's just use this standard, and that's the most that I always see in textbooks. So let's maintain that standard. Yes. Or this one, if you have a V2 and a V3, is some sort of a bi-directional. Like there we've got a V2 and a V3. It's some sort of like this signify this what we have, that you can go both directions from V2 V3, something like that. But normally on a directed graph, I think we need to investigate this and look at this very well. We need to have arrows which shows direction. That's why I've said that this one we need to really investigate this. We must have a direction which points that we are going from this to this. But normally on these graphs, when I talk of these graphs in other versions of these graphs, they will have a different name from a digraph. You will have an edge, and this edge will be bidirectional if it doesn't have any arrows from both directions. You see them when I doing discrete mathematics. They will be bidirectional, and we'll be talking of degrees of what at each and every vertex. What is the degree of this, whatever. You see it when you are doing discrete mathematics. That one, and that's where you must see these what do you call these edges, which are bidirectional. They are not, they do not have the specific direction, which means you can go from v3 to v2 or from v2 to v3, something like that. But for a digraph, we need to have this direction, something like this, which tells that we are, that's why it is directed graph or digraph. So this one, it's supposed to have a direction for E4, but we do not have it. Hope we are answered there. Yep. Then I don't know if I've got some contributions there or whatever, I don't know. Anyway, let me look at the partial order. If we say that the relation is of partial order, what does it mean? And maybe you might be asked to prove, is this relation of partial order? You'll be not told what is partial order, so you need to know what is partial order, something like that. So a relation R on a set X is called a partial order if R is a reflexive, antisymmetric, and a transitive relation. So it needs to be reflexive, antisymmetric, and transitive. Those three. So if you say, please check or verify or maybe prove if this relation is of partial order, tell us that it satisfies the rules or the whatever. For reflexive, it satisfies to be antisymmetric, it satisfies to be transitive. So it's up to you to know what is know what is reflexive, what is antisymmetric, what is transitive. So consider the relation R on set X, which is 1, 2, 3, 4, and denoted by xy is an element of R, is an element of R if X divides Y, right? So whenever X divides Y, which means here we can have 1, 2, 1, 1, 3, 1, 4, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And then after that, we need to look at we cannot have a 2, 1 because 2 doesn't divide 1. We can have a 2, 2. We cannot have a 2, 3, something like that, because 2 doesn't divide 3. So we can have a 2, 4. Then we cannot have a 3, 2, but we can have a 3, 3. We cannot have a 3, 4. We cannot have a 3, 5. That's why. And then you can have a 4, 4. We cannot have a 4, 5, something like that. All right. So the result of R is this thing that we have here. Now you need to check, is this relation R of partial order? So the first thing is to check, is it reflexive, right? So is it reflexive? Look at the elements that we have. We've got 1, 2, 3, 4, 5. So we must have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 in our relation for it to be reflexive. Let's check that. Yes, we have 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. So it's what? It's reflexive. So that's what you write here first. Then you check if it is R is antisymmetric. Then you need to look at what we have said before. Whenever you see a 1, 2 for antisymmetric, like here we have seen a 1, 2, we must not see a 2, 1. Whenever you see a 1, 3, you must not see a 3, 1. Whenever you see a 1, 4, you must not see a 4, 1. Whenever I see a 1, 5, you must not see a 5, 1. 2, 2 you can accept. 2, 4 you must not have a 4, 2. What else? Just like that. So R is antisymmetric since 2, 1, 3, 2, 4, 1, and 5, 1, as well as 4, 2 are not in R1 or are not part of what? Of R. So are not part of the relation R. So it is antisymmetric. For transitive, let's look at the issue of transitive, right? So we've got R2 is transitive since 1, 2, 2, 4, and 1, 4 are in what? Are in R. Why 1, 2 and y 2 4 and y 1 4. Why are we looking at these things to say this is transitive? Someone to say, why are we looking at these things to say it is transitive? Why are we looking at these things? Someone to tell, someone to tell. I've got Munashe Chiwai. Yes. Mhm. So where is it 1 4? This one, right? Yes. Let's go again. What else? What else? We've said that with a 1 2, and whenever you have two related something, then we must have a 1 4, right? What else do we have? What else do we have? We've talked about it. Anyway, I think that's what we really want to look at. So when you are looking at transitive, we've said that whenever you have, so having 1 1, it's not a problem, right? But now when that one is linked to something, and then we means that it means that that one, whatever, then it means one must be linked to that. So we have 1 1 and one is linked to 2, then automatically it means that we already satisfied it, because we do not need to have the third part. Why? Because one is linked to one and you do not know which one is x, y, whatever, something like that. So whenever you have a 1 1 and a 1 2, it means that already one, this one is already linked to 2. So we do not need to look at these scenarios. So the special scenario that we have here is this one, when you have a 1 2, right? This 1 2 and a 2 something, which was a 2 4, which is different. We do not need to look at this 2 2 again, something like that. But why? Because it's already linked, right? But whenever you have a 2 4, then it means this one must be also linked to 4, and we've got this one 4. So that was the only scenario, which was the special scenario that we're supposed to look at, or the special relationship that we're supposed to look at for the transitive. Otherwise, we don't have any other thing to consider there. So by doing so, it tells us that this relation is of partial order. So you put the comment. So that's R is a partial order relation. Then there is what we call an equivalence relation. The equivalence relation. What is this equivalence relation? So normally you are also not going to be told that equivalence relation is this, unless if we feel like we need to give a hint. But an equivalence relation is a relation that is reflexive, symmetric, and transitive on a set X, right? So I call it equivalence relation. So if we've got a relation which is both reflexive, symmetric, and transitive, so look at this, and so the issue is on the issue of being unsymmetric or symmetric. So partial order, you've got reflexive, unsymmetric, and transitive, but you've got reflexive, symmetric, and transitive for equivalence relation. So what you need to check is just reflexive, symmetric, and transitive. So if you look at this, what we have here, you check, is it reflexive? The set was 1 2 3 4 5. So you check, does it is it reflexive? Who else wants to check if this relation is reflexive? Wants to check if it is reflexive? That's the last thing to do for today. Not Devson, not Devson. I want someone who didn't even say a word here. Devson, not Tanaka, not Wilfred, not Mpofu. Who else? Just for reflexive. I mean, it's reflexive. I think it's very, very clear, very straightforward. Not Marvin. I think Marvin have said something. Blessed, you having the issue with your mic. Maybe you can unmute yourself. Blessed Claire. Still your mic. I can't hear you. I can't hear you. Maybe I can take Vengai there. I saw a hand by Vengai. Where's Vengai? You can unmute yourself. Yeah. Yes, even how are you? Mm-hmm. Okay. That's it, Venga. So you write it like this: R is reflexive because we've got a 1 1, a 2 2, 3 3, 4 4, 5 5 is an element of what, of our relation R. That's how you write it in shorthand. Okay, thank you for that. Thank you for that. Now we want to look at the symmetric. We want to look at the issue of symmetric. I want someone else to look at this, the issue of symmetric. Ivo Tinomku Zamasawi. You can unmute yourself. Can unmute yourself. Maybe it was a question. Okay. Was it a question or a contribution? Okay. So let's look at the issue of symmetric here. Is this symmetric or not? Let's talk. Let's talk. Okay, maybe we can have another person to try. There was someone, Valence, right? Yeah, Valence. You can try. You can give it a try. You can tell us about this. You can unmute yourself. Okay. Someone else. Someone else. Uh, Ratio. Ratio Mgan. Is it Ratio Mgan? Or maybe I can go to the next slide there. There's Shamin Muramba Kawanda Kuno. Shamin, can you try this? Ah, okay. So anyone to try, you can just unmute yourself. Because there's Miroyashe there, Miroyashe. You can try. Let's see Miroyashe. There is a hand there by Miroyashe there. Let's go on this symmetric, be it symmetric or not. Another 4 2. Exactly, that's it. Thank you for that. Maybe now we need to look at the last thing, which is a transitive. Someone to try. I think it was Chipo. Chipo, are you there, Chipo? You can give it a try, Chipo. There was Chipo there. Yes. Chipo Manika. I don't know, maybe your mic is not working. Maybe your mic is not working. Then let me just try Tanaka there, Tanaka Musirwa there. Let's do for the issue of transitive there. Mm-hmm. We have one. Okay. I've got a 1 3. I've got a 1 3. Then a what? And a 1 5. And a 5 3. Where is a 5 3? This one. Let's look at this. We've got a 1 3 there. And then we must have 3 linked to something. It's x, y linked to z, then x to z. So whenever we have xy and have a yz, and then we must have xz. So if we have a 1 3, we must have 3 something and then 1 to that something. So yes, if we if we say we have got a 1 3 and a 3 5, then we must have 1 5. Are you getting it? So we need this one, that whenever you have a 1 3 and a 3 5, also 1 is related to what? To 5. That's this 1 5. Is that making sense? Yes. What else do we have? Maybe something that we need to pick. We have a 3 1. Okay. So we have a 3 1 and then a what? A 1 5, this one. And a 3 5 again. Where is 3 5? Okay. You said we've got a 3 1 and then we've got a 1 5. Yes, yeah, exactly. Exactly. Yes, we've got this. What else? What else? I want you to look for it. I'm not seeing it even myself. I'm not seeing it. I want you to look for it. Let's help each other to look at these things. This is what we'll be looking at. Yes, we got 1 3 3 1 2 4 4 2. Someone is saying this on YouTube. Let's. Is there something else? Let's talk about it. Yes, this one. Yes, this. There's also what? So let's talk about this. You are saying there's a 2 4 there. And yes, yeah, and 4 related to 2, then 2 is related to itself. Ah, okay, yes, yeah, yeah, that one exactly. What else? If we exhaust, yes, yes, a 1 5, then a 5 1, and then a 1 1, right? Yes, and then it exhausts all the list, right? I think that's all what we have there. So that's how you comment on this one. So in short, that's why you've seen that RS transpose whenever we have X, Y, Y, Z, then which are in this relation, then XZ is also in the relation what in the relation R. So which means that R is an equivalence relation. So normally that's how you write your answer here. That's how you write your answer and put the conclusion that R is what? R um is an equivalence relation. So that's all on relations. So if there is any question on relations, please you need to ask now. Otherwise, we do through a discussion. I don't know, Marvin, if it is a hand or it's an odd hand. Is it a new hand or it's an odd hand? Okay, it's okay. Venga, you want to say something? Okay, okay. So maybe what I'll do is we'll have another tutorial tomorrow. Do you have any tutorial tomorrow? Do you have any tutorial tomorrow? So, so okay, so what we are going to do is we're going to have another tutorial tomorrow, and then on that tutorial maybe we can now try to move fast. Why? Because these things were a little bit problematic. We needed to take our time to cover this, and then on other things I think it will be a little bit easier. So um for today I think we can call it a day, unless if the questions, otherwise we can call it a day. Do we have any other question? Yes, yes, the last slide. Okay. I'm waiting for your question. Okay, we've got 1 5, and then 5 is related to 1, and then it automatically means 1 is related to 1. Okay, the relationship that we've got an X and a Y and a Z. Okay, the XYZ is there by the fact that whenever you have this 1 1 here, it means that this is X, this is Y, something like that. So yes, it doesn't matter if this one we have got 1 1. I think this one, it doesn't matter if we've got a 1 1 there. It doesn't matter there. Yes, you are not going to, you are not going to disqualify that. Why? Because we've got a 1 5 and a 5 1. By that virtue, it means 1 is related to 1. Then it completes that. Then it maybe where it is very clear is when you have a 1 3 and then it 3 something which is not a 1, and then 1 linked to that. That's when you clearly see this xyz. But remember, we always say that this one what you have, it doesn't mean that one is just from the same x that you are thinking of, because this one what we have and this one, for us to pay it, it means this one is coming from somewhere and this one is coming from somewhere. It's only that we are using the same set, but we are crossing it as this is part of x, this is part of y. It's not this one the same whatever, something like that. So if you take it that way, you will see that we will end up having the xyz part of it. Yes. So what I need to do is to go. That's what I need to do. So guys, mm-hmm, mm-hmm. Or she, no, she was saying we have got a 1 5 and a 5 1. So why do we say having a 1 1 completes the transitive part? Because for transitive we need to have x y like 1 3, and then we've got 3, maybe 3 something, like you've got a 3 5, right? Which is now this y linked to z, which is what, which is 5. And then we say that after that 1 must be also linked to 5, which means we must have a 1 5, this 1 5 that we have here, something like that. So she was saying, why are we end up saying 1 5, then 5 1, and then say 1 1? Oh, that was the question there. So guys, have have a good night. I'm out. We talk later for any other thing. You're welcome.